To ensure the DC-DC converters work in a continuous conduction mode, the selection of the suitable inductor size is very crucial. To design the inductor, there are two approaches you can choose. First, you already set the percentage of the ripple inductor current. For a buck converter, you can use these following equations. You can use either equation 1 or 2 for your calculation. Nevertheless, if the percentage of the ripple inductor current is undecided, we need to identify the size of the inductor using the critical inductor value. As usual, I will show you how to design the inductor of a buck converter using the critical inductor value. After watching this video, I hope you can try to design the inductor of boost and buck boost converters using the same procedures. In total, there are 10 steps to design the inductor. First, we need to choose one delta ILT equation. Since the second equation has only one voltage parameter, thus I will choose this equation for this procedure. After choosing the equation, we need to rearrange the equation to obtain the inductor equation. Next, we need to shift our focus to the waveform and equation of the inductor current. To determine the critical inductor value, we need to consider the critical condition of the inductor current waveform. It happens when the minimum amplitude of the waveform equals to 0. This condition is considered critical because the converter will work in the discontinuous conduction mode if the minimum current is less than 0. Therefore, we need to move the inductor current waveform downward until the minimum current equals to 0. According to the new position of the waveform, the new value of the minimum amplitude is equal to 0. Thus, the ripple inductor current is now equals to 2IL. And therefore, we can rewrite the inductor equation as follows. Eventually, this equation represents the critical inductor equation. Since the equation consists of the average inductor current, thus, we will focus on the average current of the converter. To show all average current in the circuit, you must remember that in the DC system, the average current of a capacitor is always 0. Thus, we can label the average currents as follows. To analyze the average currents easier, we must consider all power switches in the converter are turned off. Next, we can apply KCL at this node to obtain the inductor current equation. Eventually, we can see the average inductor current is equal to the output current. For the next step, we will substitute the output current or supply current, if existed, using Ohm's law or power equation. Since the equation consists of the output current only, therefore, we just need to apply the Ohm's law. Later, we need to eliminate the voltage parameter in both equations. First, we need to combine the equation of the critical inductor and average inductor current together. Second, if the equation consists of two different voltage parameters, we need to apply the output voltage equation to obtain one type of voltage parameter only. Therefore, the equation will change as follows. Finally, the actual inductor value can be calculated by increasing the critical inductor value by 10% up to 20%. It is to ensure that the converter will work in the continuous conduction mode.